Introduction. So before I forget, I would like to thank everyone who was involved in organizing this workshop, especially Professor Kwak and Ms. Kim, for the hospitality. I really enjoyed every talk at this workshop. I enjoyed every meal, and I enjoyed the excursion yesterday. And it was a very nice experience to be here in Jeju Island. Okay, so the purpose of the first talk was to define the discriminant of a section of a vector bundle. And I also posed some questions related to the discriminant. And my original plan for the second talk was to state my main theorem and give an detailed proof. But my approach is quite straightforward. And after giving the first talk, I thought it may be beneficial for the audience if I explain why I got interested in discriminants. So here is the list of topics I'm going to talk about today. So I'll take a brief look at the definition of a discriminant of a vector bundle. And I would like to present two known results related to the discriminants of vector bundles. One of the main purposes, as I said, was to tell you why I got interested in discriminants. So more precisely, what I'm going to talk about is tensor eigenvectors, which can be viewed as a generalization of an eigenvector of a matrix. And then each tensor is associated with a scheme, which is called the eigenscheme. So if the tensor is generic, eigenscheme consists of a finite number of points, and you can ask when or for which tensor, or you can also ask the set of tensors whose associated scheme is non-reduced. Okay, such a set is called the eigendiscriminant. Okay. And a question you might want to ask now is, so what the relationship between the title of this talk and the eigendiscriminant? And the irreducibility and the degree of the eigendiscriminant can be actually obtained from the discriminant hypersurface of a certain vector bundle, namely a twisted tangent bundle. So that's the connection between the eigendiscriminant and the discriminant of a vector bundle. Then I'm going to state my main result. So I studied a discriminant hypersurface of a global section of a so-called Schwarzenberger bundle. So a Schwarzenberger bundle or Schwarzenberger type bundle is rank n-1 vector bundle or Pn-1, which can be viewed as an extension of a tangent bundle or twisted tangent bundle. And of course, you may ask, so why did I pick a Schwarzenberger type bundle? So I would like to explain why I care about this vector bundle. Oops. Okay, so I just wanted to recall what the definition of the discriminant of a vector bundle is. So let's suppose it's a vector bundle on rank R on Pn-1. Okay. So then delta E is defined as the set of global sections whose zero scheme is singular. It could be the empty set, but if it is not an empty set, then we call delta E the discriminant variety of a global section of E. So I thought that's a little bit too long, so from now on I just call it the discriminant variety of E. And the last time I posed some questions, for example, how big the discriminant variety is, or is the discriminant variety irreducible or reducible? And what about the degree of the discriminant? So these are kind of examples of questions you can ask about the discriminant variety of a vector bundle. And I would like to discuss two theorems, two results related to the discriminant of a vector bundle. So the simplest vector bundle on Pn-1 is the direct sum of line bundles. So I don't know how to pronounce the name, so I just say, so these two gentlemen worked on the discriminant of the direct sum of line bundles, and they proved it is an irreducible hypersurface, and they also calculated the degree. So their formula for the degree is a little bit different. So this is the formula I found, but this has been already done in 2014. So another result is about the so-called Horrocks-Mumford vector bundle. So the Horrocks-Mumford vector bundle is basically a stable rank 2 vector bundle on P4, whose Chern classes are 5 and 10. So this is essentially the only known indecomposable rank 2 vector bundle on P4 over the complex numbers. And the dimension of the space of global sections is equal to 4. And if you pick the generic global section of the Horrocks-Mumford bundle, you get an abelian surface of degree 10. However, there are a list of degenerate Horrocks-Mumford surfaces, and those degenerated cases were already classified by Balto, Hulick, and Mua in 1987. They also described the discriminant of the Horrocks-Mumford bundle. So it is an irreducible hypersurface of degree 10 in P3. So I was curious how the equation looks like, so I spent some time this morning to find out the equation for this for the hypersurface, or in this case the surface. So let's suppose A0 up to A3 are homogeneous coordinates of the space of projective space of global sections of the Horrocks-Mumford bundle. Then the hypersurface, discriminant hypersurface, is defined by this degree 10 homogeneous polynomial. Okay.
Did you look at the singularities of that hypersurface?
No, not yet. So what they did is actually, so they found the stratification and in which strata they can find which degenerate case. So it's well studied. Okay. Now I would like to discuss an eigenvector of a tensor. So in this slide, I consider only the tensor product of these copies of Cn. So if D is equal to 2, it's just a square matrix, and if D is equal to 3, you have a cube. Okay? And let's suppose A is an arbitrary tensor in this tensor space. And then you can associate this tensor with the following homogeneous polynomial of degree d minus 1. Okay, I'm not going to explain how this, but I'm going to explain in an example, but hopefully it's clear how you get these homogeneous polynomials. Okay, and I would like to denote phi of a of x, the vector valued function whose ith entry is equal to this homogeneous polynomial of degree d minus 1. Okay. So, for example, if d is equal to 2, phi sub a of x is just a times x. Okay. What happens if n, for example, n is equal to 2 and d is equal to 3? So you have a 2 by 2 by 2 cube, right? So you have this 2 by 2 by 2 cube. So then what I'm going to do is just I fix one of the directions and cut this cube into 2 pieces. And then you have 2 square matrices. Then I consider this quadratic binary form for the first, and then you do the same thing for the second matrix. Okay. So this gives you 2 quadratic binary forms that form the vector bundle, vector valued function phi sub a of x. So how do you define eigenvector of a matrix? So if you have a square matrix A, so a non-zero vector B is an eigenvalue if and only if and A times X is equal to some scalar multiple of B itself, right? Okay. So the notion of an tensor eigenvector was introduced by 2 people, Le-Ken Lim and Li-Kun Ki, separately in 2005. So the definition is just use the vector valued function I just defined in one slide ago. So let's suppose A is a given tensor, and if there exists a scalar lambda such that phi sub A of B is equal to lambda times B, then we call B an eigenvector of A. Okay, so this is just a very natural generalization of eigenvector of a matrix.
In definition of phi homogeneous polynomial, you just take the first index.
That's right.
Yes. Is it enough to?
Yeah, first index, and then replace each tensors by variables and then multiply them together.
Yeah, this A is not symmetric matrix.
Not necessarily, yeah, regular tensor. So any tensor.
Okay. So you just see the one direction.
That's right. That's right. So I chose the first one, the first direction. Okay. So it may be very easy for you to see it, but I just state the following proposition just in case. So if B is an eigenvector of A, then its scalar multiple is also an eigenvector of the same tensor. So that's true for the matrix, but that's also true for general tensors. And the proof is very simple. So the key fact is the vector valued function consists of homogeneous polynomials of the same degree. So the reason I wanted to include this proof, because now you can see, so this mu times B is a scalar multiple of B, but then the scalar you can use to define eigenvector changes. Okay, so the problem is the eigenvalue is not well defined in this case. Okay. So if you teach linear algebra for undergrads, and how would you teach to find an eigenvector? So one way is you set up, so you choose some lambda and you set up Ax is equal to lambda x, and you compute the characteristic polynomial and find the roots. And once you find the roots and you pick one of those and plug in X is equal to lambda x and find the eigenspace, right? But as I said here, so the concept of eigenvalue is not well defined. So I don't want to use eigenvalues to find eigenvectors of the tensor. So what I'm going to do. So the key observation is V is an eigenvector of A if and only if phi's of A of V and V are linearly independent. So that means if you concatenate these two vectors and take the 2 by 2 minus, you get 0. Okay. So that means you can define the set of eigenvectors by using determinantal ideal. Okay, so let's suppose R is Syzygian adjoint x1 up to xn, and x is the column vector consisting of the variables x1 through xn, and I denote by I sub a the ideal generated by the 2 by 2 minus of this n by 1 matrix obtained by concatenating v sub a of x and x. And V is an eigenvector if and only if V sits inside the variety defined by this I sub A. Okay. So since if V is an eigenvector of a tensor if and only if its scalar multiple is also an eigenvector of the same tensor, so I would like to identify these two eigenvectors, and I would like to define a so-called an eigenpoint. So if V is an eigenvector of A, then we call the equivalence class of this V an eigenpoint of A. And you can collect all eigenpoints in the form of variety, okay, which I call the eigenvariety of the tensor A. Then, as I said, you can define the determinantal ideal. So there is the scheme associated with this ideal, which I call the eigenscheme of the tensor A. So let's discuss a very simple example. So I have a tensor of this form. So E1 O times E1 O times E1. So our tensor is just has one term, and in order to get phi sub A of x, all you have to do is just hide the first component, and then replace E1 by x1 and then E1 by x1 and multiply them together. So you get x1 squared. But since you have only one term, so I'm sorry, this is phi sub A, 1. The other components are all 0. So phi sub A consists of x1 squared and 0 and 0. So now I would like to find out where we have the eigenvectors. So I formed 3 by 2 matrix by concatenating these two vectors. So, and now I have to take the determinant, 2 by 2 minors. So the ideal is generated by, ideal of the tensor is generated by x1 squared times x2 and x1 squared times x3. And if you compute the primary decomposition, you get the intersection of the ideal generated by x1 squared and the ideal generated by x2 and x3. Okay, what does it mean? So that means the eigenscheme consists of two components. One is a double line defined by x1 squared, and the other one is the single point defined by x1 and x2. Okay, so the previous example tells us that eigenscheme could be non-reduced, and the eigenscheme could have a positive and dimensional component. But if A is generic, then the scheme consists of a finite number of points and non-reduced. So you might want to know how many points you're going to get, how many eigenpoints you're going to get. So Cartwright and Sturmfeld gave the formula for the number of eigenscheme for a generic tensor, which is d minus 1 to the n minus 1 divided by d minus 2. So if d is equal to 2, I'm going to use the formula in the on the right. Okay, for example, if d is equal to 2, so you expect n, and you actually get n. And if you consider a binary tensor, then you get a 2 by 2 matrix, and if you take the determinant, you get a degree d polynomial. So you expect d roots, so that's why d to d is equal to d. And the first non-trivial case is the case where n and d are both 3. In this case, you get 7. Okay, so I would like to prove this equality by means of an example. Okay, so here I have a little bit more complicated tensor. So okay, so you have a 3 by 3 by cube, and the only non-zero entries are on the main diagonal, and they are all 1. Okay, so you can also think of this as a symmetric tensor, or homogeneous polynomial x1 cubed plus x2 cubed plus x3 cubed. Okay, then phi sub a of x is equal to x1 squared and x2 squared and x3 squared. You can play the same game as before. So now you concatenated these two vectors, and I computed the 2 by 2 minus of this 3 by 2 matrix, and you get these 3 cubics. And of course, all you have to do is just to plug those in the Macaulay 2 or some computer algebra system and compute the primary decomposition. So the primary decomposition tells me there are 7 components, 7 points, and these 7 points are defined by these linear forms. Coordinates, and linear forms. And if you draw this line point configuration, you get. So this is P2. So we see this configuration on Wednesday.
I'll see it again today.
Right. So I'm
it this way.
Yeah. Oh, thank you. Yeah. So that's right. Okay. So we got 7 points as expected. Good. And the question is, now we understand the concept of an eigenscheme and eigenvector of a tensor, but so what is the relation between the title and the eigenscheme? Okay. So the eigenscheme turns out to be the zero scheme of a global section of a twisted tangent bundle. Okay. So the tangent bundle of Pn-1 is obtained by the Euler sequence, right? So, but the Euler sequence is also a part of Koszul complex. So, for example, tangent bundle twisted by OD-2 can be obtained as indicated in this diagram. Okay. So H0 of the bundle in the middle is CNO times the D minus first symmetric part of CN dual. Okay, so that means every element in this space can be built as a collection of n homogeneous polynomials of degree d minus 1. Okay, so that's basically phi sub a for some tensor a. Okay, so now I'm sending that element to the cohomology group of the twisted tangent bundle by using wedge x. So this is the space of global sections of tangent space twisted by OD-2. But taking the wedge is just equal to taking the 2 by 2 minus of the n by 2 matrix obtained by concatenating phi's of A and X, right? So that tells us the eigenscheme of a tensor in the tensor product of these copies of Cn can be identified with the zero scheme of a global section of the twisted tangent bundle. Okay. And now you can use the invariance of the twisted tangent bundle to count the number of expected number of eigenpoints. I mean, all you have to do is to compute the top chunk class of this bundle. That turns out to be the same as in the theorem of Cartwright and Sturmfeld's. Okay. Now, so we know the eigenscheme of a generic tensor consists of a certain number of points, but we also know there are tensors whose zero scheme is non-reduced, has a positive component. So I would like to collect such unexpected tensors to form a variety. Okay. So more precisely, delta sub n comma d is the set of equivalence classes of tensors whose eigenscheme is singular. So I have to also close this up. So it's a risky closure of such a set. And you can ask the same question as before: how big this object is, or what is the degree of this object is, and so forth. So by the way, so we decided to call this object the eigendiscriminant. And the proposition in the previous slide tells us the degree of the eigendiscriminant and the degree of the discriminant of the twisted tangent bundle must be the same. Okay, they are sitting in the different space, but the discriminant of the twisted tangent bundle can be built as a linear section of the eigendiscriminants. So all you have to do is to compute the degree of the discriminant of the twisted tangent bundle. Okay, so now I would like to take a 1 minute or two to discuss a very simple example. So what happens if d is equal to 2? So if d is equal to 2, the eigendiscriminant is defined as the discriminant of the characteristic polynomial of an n by n generic matrix of n squared variables. Okay, so what do I mean by this? So this is a very toy example. So let's consider a 2 by 2 matrix of 4 variables, a1, 1, and so forth. And then you can compute the characteristic polynomial, which is t squared minus trace of a times t plus the determinant of a. And of course, the discriminant is trace of a squared minus 4 times the determinant of a, which is an irreducible polynomial of degree 2. Okay? And in general, the degree of delta n2 is equal to n times n minus 1. And the question is, what is the degree of delta n comma d if d is bigger than or equal to 3? Okay? So this is what I would like to answer towards the end of this talk. So the reason why I wanted to work on tensor eigenvectors was in the matrix case, the square matrix is not diagonalizable if and only if the ideal associated with this matrix is not radical. So there is a clear correspondence between linear algebra and commutative algebra. So my original hope was, if I study the eigenscheme of a tensor, especially that if the tensor, the eigenscheme is non-reduced, I might be able to gain some understanding of unexpected tensors. So that was kind of the motivation. And one way to capture this aspect is to consider the eigendiscriminant. Okay, so now it's time to state my main theorem. So my main theorem is about the discriminant of a Schwarzenberger type bundle. So first of all, I would like to define a Schwarzenberger type bundle. So you have this n minus 1 plus k by k matrix. So you can easily see what the entries are. So if you see nothing, that means the entries are 0. Okay, and I consider the co-kernel of this sheaf morphism. Okay, so now if you take k by k, or maximum minus of this matrix, and you can easily see the radical of the ideal of generated by k minus of this matrix. It's the irrelevant ideal. So that means this sheaf morphism is actually an injective vector bundle morphism. So that means the co-kernel of this phi is a vector bundle of rank n minus 1. Okay. So as I said in the beginning, I was interested in this vector bundle because this is a natural generalization of the tangent bundle twisted by O minus 1. And this vector bundle, it's called a Schwarzenberger type bundle, or sometimes STB. So let me briefly mention some information about this vector bundle. So you can compute the Chang class by using the exact sequence. And also by definition, E sub k, and hence its twist by OD, where D is a non-negative integer, is globally generated. Okay, that means if you pick a section of this vector bundle, it is expected to be non-singular. So I would like to count the number of points you get. So all you have to do is, as before, just computing the top Chang class of this vector bundle. This turns out to be this formula. Okay, so there are two cases I would like to focus on. The first one is the case where k is equal to 1. So it's just the twisted tangent bundle case. And if d is equal to 1, so you get this single binomial coefficient as the top Chang class. And here is the main theorem. So the discriminant of E sub k of d is an irreducible hypersurface of degree. So I found the degree formula, which looks a little bit complicated, and it is actually complicated. So I don't want to go in details, but all I did was, at least to get this formula, all I did was the same idea I mentioned at the end of last talk. So if you have a hypersurface, if you want to count find the degree, all you have to do is poke this hypersurface with a generic line and count how many times this line meets the hypersurface. Okay. Then if you pick one point on the line, you get the corresponding eigenscheme, which consists of a finite number of points. So if you move this point downstairs, so you get a curve. And the line meets the place where the line meets the hypersurface is exactly the curve has a branching point. Okay, so you can count the number of intersection of the line and the hypersurface. Just all you have to do is to count, to use the Hilbert's formula to find the degree of the ramification divisor. Okay, so the first term comes from the degree of the map from the curve upstairs to the line. And the middle term has something to do with the genus of this curve. Okay. And the question is, how can I find the genus of the curve? I thought there is a formula to tell me what the genus really is, but I was not able to find it. So all I did was the curve is obtained at the dependency locus of two sections. So that means you have a map from some line bundle, to direct sum of two copies of line bundles to E. So I flipped it and I considered Eagle-Northcott complex. That complex is going to be exact, so I use this exact sequence to find the genus. So as I said, E1 twisted D minus 1 is equal to the tangent bundle twisted by D minus 2. So this bundle has something to do with the eigen discriminant, right? Okay. So we computed the degree of this case. It turns out that the degree formula is n times n minus 1 times d minus 1 to the n minus 1. So if d is equal to 2, then you get n times n minus 1, which is the degree of the discriminant of the characteristic polynomial of a matrix. So even if the formula looks very complicated, in this case, the formula is very simple, and I thought this is very beautiful. So there's another simple case. This is the case where d is equal to 1, and then the degree formula for the discriminant is equal to this. So you have a bunch of binomial coefficients. Okay. So one of the reasons why I was interested in Schwarzenberger type vector bundle is it is a natural extension of the tangent bundle or twisted tangent bundle. But there is another reason why I was interested in this bundle. So that's something I would like to explain in the next slide. So now let's consider a sheaf morphism from this direct sum of line bundles to this direct sum of line bundles. And you can consider the degeneracy locus of this sheaf morphism. Namely, this is the set of points in Pn minus 1 where the rank of phi is less than or equal to k, so drop at least by 1. And if phi is generic, we know the codimension of the degeneracy locus is equal to n minus 1. That means zero-dimensional scheme. And this is also non-singular. And the number of points in this scheme is equal to n minus 1 plus k choose n minus 1. So again, you have a set of points, but if you move phi around, you might get some phi which does not consists of exactly this number of points. Okay, so I would like to collect such feeds and form a variety, which I denote by delta sub k. And it turns out that this delta k is an irreducible hypersurface of multi-degree, and degrees are all the degrees of STB twisted by O1. Okay. So what is the idea behind this? So let me explain that here. So I'm going to write down the matrix. So this is n minus 1 plus k by k plus 1. So obviously you have k plus 1 columns. Okay. So each column can be viewed as viewed as the space of global sections of this direct sum of line bundles. Okay, so that means phi can be viewed as an element of the multi-projective space. So of course we have k plus 1 factors. But there is also an exact sequence. So by using this exact sequence, you can consider the projection from H0, O1, O plus n minus 1 plus k to H0 of EK of 1. Okay, so now I can use this projection to project delta sub k to delta of E sub k twisted by 1. Okay, so then you can describe the fiber, and you can easily prove that the fiber is irreducible, and I proved this is irreducible. So delta sub k is also irreducible. And this is a hypersurface, and this is a the defining equation should be a hypersurface of a polynomial of multi-degree, right? And if you restrict, so the first factor you get this degree, and so forth. So that's how I proved the theorem. And I should have said before, oops, no, I have to go back, yeah, here. So I consider only linear factors in this slide, but you can also consider parts of each coordinates, and you can play the same game to prove the irreducibility, and you can also get the degree formula. And you can also find the discriminant of a set of points whose ideal is determinantal. Okay, so that's the reason why I wanted to study Schwarz-Welger type vector bundles, and it's discriminant. Okay. So I often go to a concert or some sort of event, and either at the beginning of the event or at the end of the event, typically the people ask us for a donation. So they typically say, how can I help you? Okay, so this is kind of the slide. So there are lots of questions you can ask about the discriminant. One of the problems you may be able to help me or help somebody else is to develop an effective algorithm to compute the discriminant. So I have a stupid algorithm to use. It's a very greedy algorithm. It's not very effective. For example, I tried to compute the discriminant hypersurface of tangent bundle twisted by O1. Okay, so the space of the global sections of such this bundle is equal to 15. Okay, so the discriminant hypersurface is defined by a homogeneous polynomial of, in this case, of degree 24 in 15 variables. And I was not able to find the equation. I'm not able to find means I was not able to finish the computation because of the capability of my laptop. So my question would be, so how can you compute the discriminant faster? That's one question. I think a very important question to ask and to answer. And so what I did instead was I have a huge space, and I only considered a tiny subspace of the space. So for example, I cut the space by the subspace spanned by ax1 cubed plus bx2 cubed plus cx3 cubed plus d times x1, x2, x3, which can be built as a P3. So I cut the whole space with P3 and I see what I get. So what I get is the surface, not irreducible surface. It's the surface which consists of 6 double planes and a degree 12 irreducible surface. So this is a picture of the irreducible surface of degree 12. And so if you have some idea of how to compute the discriminant faster, please let me know. And thank you very much for your attention.